Hello people, welcome to Gurukula. I'm Jai. I'm working for R.M.K College of Engineering and Technology under the Department of Electronics and Communication Engineering. So here in our previous videos, we are discussing in detail about the various services offered by the data link layer. And especially in the first few videos, we might have discussing what are all the various physical layer addressing, and then in our previous video we might have discussed in detail about the parity bits and then the cyclic redundancy check. So we are in the process of discussing, or we are sequentially discussing the various error detection codes that is available in communication networks. So this video we are going to cover an topic that is what we call it as cyclic redundancy check, so which is also called as an error detection code, and in short it will be called as CRC code. So we will see how the CRC codes is being performed at the transmitter side and as well as at the receiver side, what's the algorithm, and then what are all the various things that we can understand about the cyclic redundancy check code in this particular video. So now without any further ado, let's get into the topic. So we are discussing the various error detection codes and then the error correction codes, and as of previous videos are concerned, we might have already discussed the functioning of parity bits and then the checksum. So if you have not yet watched the video on the parity bits and then the checksum, I will leave the link for the video on the I button and as well as the description section. So please check out the previous videos that has been posted in Gurukula. So this video we will be completely focusing on the cyclic redundancy check code, which is in short we call it as CRC codes. And then in the subsequent videos we will be talking about the Hamming code. So subsequently, when completing the Hamming code, we are completing the first module of this communication network series. So with this note, let us see what a cyclic redundancy check code is and what is it all up to. So this is an algorithm for the cyclic redundancy check or CRC code. So in order to perform a cyclic redundancy check, it is not so tedious, or the algorithm is so simple that it is going to perform a very well known, or whatever we have studied in the good old days, that is what we call it as long division method. So your cyclic redundancy check is also going to be performed by using the long division method over here. So in order to perform a long division method, you will have three components in hand so as to perform the cyclic redundancy check. So as you could see over here in the cyclic redundancy check algorithm, so this is what happens at the transmitter side and this is what happens at the receiver side. So in order to perform a cyclic redundancy check, you need a data word. Your data word is nothing but the actual data which you wanted to transmit from one point to the another point, and along with the data you are going to add few redundancy bit, and here I am going to call these redundancy bit as CRC bits, which you wanted to append to your data word so that you can process the CRC algorithm, and finally you will get a code word over here. Your code word is nothing but your data bits appended with few redundancy bits that we got out of CRC algorithm. These redundancy bit will be given by the generator, which actually performs the CRC, and then the bits, that is the output we getting from generator, will be added to the data bit, and then your code word will be transmitted over an unreliable channel or medium. And then we will have a third part, that is what we call it as a divisor, which is commonly shared between transmitter and then the receiver over here. So we will see, so these are all the three important components which we need to perform a CRC at the transmitter side and then the receiver side. The first one is the data bit, and the second one is the CRC bit, and then finally third one is the divisor to perform the long division method. So just to put it in a very simple way, we are going to perform a long division method what we have already come across in our schooling days. So here we are going to put our data bits over here, and then our data, along with our data bits, we are going to add few more bits, that is what we call it as CRC bits, and then I am going to divide this by using a commonly shared divisor over here, so that I will be getting a quotient on top over here. While performing a long division method, I am going to get a remainder over here. So what I'm going to do is, as far as CRC is concerned, the quotient is completely useless. So we will be discarding the quotient part and we will be taking only the remainder. So based on the remainder, here the remainder is also called as syndrome at the receiver side. So before jumping into the working of the cyclic redundancy check, there are two important things which we have to make it very clear before entering into an example of cyclic redundancy check. So what are all those two things? The first one is the polynomial representation of the bits. So for the sake of theoretical discussions, we will take up the example in ones and zeros for the sake of understanding the process of cyclic redundancy check that is happening at transmitter side and then the receiver side. But actually the system will take it as an polynomial representation. So what is polynomial representation? Let us assume that this is what the data which I wanted to transmit. So how do I represent this in a polynomial form? So I can easily represent this as polynomial form. As such, the first position of the bit is nothing but that represents the polynomial x to the power of 0. And similarly, the second position is represented, or it takes the polynomial representation of x to the power of 1. So similarly, it goes on x to the power of 2, x to the power of 3, so x power 4, x power 5 and x power 6. So this is what the polynomial representations of these bits. So actually the 1 is nothing but the coefficient of x to the power of 0. So this bit, this 1 will be the coefficient of x to the power of 1, as it is clearly mentioned over here, as you can see. So 1 is a coefficient of x to the power of 0. So that is how I can write the entire component over here. So when I multiply, I will get 1 into x to the power of 6, I will get x to the power of 6, 0 into anything becomes 0. So 0 into anything becomes 0. I can neglect all the terms which has the 0 term, and then here I have 1. So this can be written as x to the power of 1, which is again I can write it as 1. So 1 into x to the power of 0, which gives x to the power of 0. Anything to the power of 0 is 1. So I can write that as 1. So now this is the polynomial representation of the binary data which is represented over here. So that is what represented in this particular short form also. So this is how and binary bits will be represented in polynomial representation. So why do we need to understand this polynomial representation? As I already said, the system will perform the cyclic redundancy check algorithm in terms of polynomial representation. But here in this video, we are going to perform the CRC as such in the binary form itself, so as to get the better clarity of what is happening inside the CRC transmitter algorithm and then the receiving algorithm. So this is the first thing which we have to keep in mind. And the second one is, we will have to understand the relationship between the bits in CRC. So as I already said, you will have a data bit. You will have a data bit, and then your data bit will be appended by few bits of CRC, and this is what will be long division performed by using a divisor over here. So these are all the three main components that is required to perform a cyclic redundancy check. Fine. So how many number of bits of data is required and how many number of CRC bits is required and what divisor polynomial I have to choose, everything should have a relationship. We cannot go for any random number of bits that can be added to the data. So everything depends upon the number of bits in the data over here. So if I assume that my data is of k bit long, if my data is of k bit long, then the number of bits that I allocate for CRC is k minus 1 bits. Your number of bits that I have to add for CRC is k minus 1 bits. So what about the divisor? Your divisor must be, the highest polynomial of the divisor must be x to the power of k minus 1. So the coefficient of x to the power k minus 1 should always be equal to 1. It cannot be 0 over there. So in order to make it very clear, let us take this particular example. The numbers whatever you can see over here in the blue shaded area is what we call it as the data word. So how many bits I have in the data? 1, 2, 3 and 4. So which in case represents, we have k is equals to 4. I have 4 bits of data to be transmitted. So here in our example is concerned, your k value is 4. Fine. So for 4 bits of data, how many CRC bits I need? I will have k minus 1 bits. So here in our example is concerned, so 4 minus 1, 3 bits of CRC is required. So that is what the 3 bits of CRC is appended to my data. Fine. So now coming to the divisor. So this is what the divisor that is being used for generating the CRC. So what is the CRC? I should have the maximum polynomial is x to the power k minus 1. So x to the power of 0, x to the power of 1, x to the power of 2, x to the power of 3. As you can see, the highest polynomial is x to the power k minus 1. So x to the power k minus 1, in our example it is 4 minus 1. So we should have x to the power of 3. So the highest polynomial is x to the power of 3. So that we can say that this is a valid divisor for performing the CRC check. So with this basic relationship between the bits that are available in CRC, now we can free to go for taking up an example problem. So what I will do is I will just work out the example over here. So it is already worked out over here, and simultaneously I will go with an step-by-step operation on the right hand side, so that the people, those who struggle to understand what is there on the left hand side, could follow up me on the right hand side what I am going to discuss now. So initially I know that this is what the data word which I wanted to transmit. So now what I will have to do, I am going to perform, I need 3 different things to be followed. So I am going to perform a long division method. CRC will be performed by using a long division method. So in order to perform a long division method, I need a data, I need few bits of CRC, and then I need a divisor polynomial for performing a long division method. So the data is already given. So data is nothing but 1, 0, 0 and 1. So that is of 4 bits long. So I can take k is equals to 4. So what should be the amount of CRC bits which I need? So it should be k minus 1 bit long. So it is k is equals to 3. So I need 3 bits of CRC to be appended along with the data. So the data is already available, that is 1, 0, 0, 1, and what is the CRC? That is 3 bits long, and initially I will be adding the values of CRC, I will be taking it as all zeros. So now I am going to long divide this by using a divisor polynomial. Your divisor polynomial should be a maximum polynomial, that should be over here is x to the power 4 minus 1, that is x to the power of 3. So I can take the divisor polynomial as 1, 0, 1, 1. So this is x to the power of 0, this is x to the power of 1, x to the power of 2 and x to the power of 3. So I can see that the maximum polynomial of the divisor is x to the power of 3, and that is the coefficient of x to the power of 3 is 1. So I can say that this is an valid divisor. So for the example concern, I will take the same divisor itself, and keep in mind that we do not have the freedom of choosing the divisor polynomial of our own freedom. So there are certain standards and there are certain characteristics that has to be satisfied while selecting the divisor polynomial. So which we will be discussing in a minute. As of now, I will take this particular divisor polynomial. So just remember that you cannot take the divisor polynomial on your own. You will have to choose the divisor polynomial based on certain characteristics which we will be discussing in a minute. Fine. So how will I have the number to divide, and then I have which number I have to use to divide this particular bit. So now it is good to go to perform a long division method. But there are 2 main differences. Wherever you perform a multiplication operation in long division method, here you will have to perform a logical AND operation here in CRC. And then especially wherever you perform subtraction operation in long division method, here in CRC you will have to perform an XOR operation. So this is what you will perform in long division method, and whereas in CRC you will have to perform this particular operation. Correct. So with this note, let us see how this particular example is being solved. So this is what my data is, and this is what my CRC bit is, and this is what my divisor is. I think you are all clear up to this particular step. So now what I will have to do is I will have to go for the long division method. So I will go for 1 times. So for 1 time, I will usually in long division method we will perform a multiplication, 1 into this. We will perform a multiplication. So since this is an CRC, we will have to perform an logical AND. So logical AND 1 and 1 will give you 1. So actually you will get the same value over here. correct? So 1 0 1 1 is what I get after performing logical AND operation. So now wherever I perform subtract, actually in long division method we will be performing subtraction between these two bits, but whereas here in CRC is concerned, we will have to perform the XOR operation. So what do I get if I perform an XOR operation? In XOR operation, if two bits are same, I am going to get 0, and if two bits are different, I am going to get 1. So that is what we will have in XOR. So with this I have the same bit, so I will write it as 0. Again I have a same bit, I can write it as 0. Again I have different bits, I can write it as 1. Again I have a different bit, again I have a same bit, so that I can write it as 0 over here. So here you can exclude this particular first value, and then as per long division method you can bring down this particular 0. If I bring down this particular 0, that will count up to 0 1 0 0. So now if I encounter 0 over here in the most significant bit, so if MSB is equals to 0, then what I will have to do? I will have to add a 0 on the quotient, and then I will have to perform the AND operation. So 0 AND operated with any particular bit, I am going to get all zeros, so I am going to get all zeros over here. So if I perform this, again I will have to perform XOR operation over here. If I perform XOR operation, I will get 1 0 and 0, and then again I can bring down this particular 0 over here. Now what I can do, now there is the most significant bit is not a 0, so that I can go for 1, again perform logical AND operation between this 1 and this particular divisor, so that I will get 1 0 1 1. So again I will have to perform an XOR operation for this, so that I will get 0, here again I will get 0, here I will get 1, here again I will get 1. So I can neglect this particular bit, and then I can bring down this particular 0 over here, so I can bring 0 here. Now again I have experienced 0 in the MSB. So if the MSB is 0, then again I will have to add a 0 over here, and then again I will have to perform an AND operation between 0 and then the divisor polynomial. So that will give me a value of all zeros over here, and then now I will perform the XOR operation. So if I perform XOR operation, I will end up with 1 1 and 0. So there is no more bits to bring it down, and usually we will be neglecting this particular value. So neglecting that, this is what my remainder is. So this is what the remainder that we have obtained by performing the cyclic redundancy check. So this is what will be actually performed in the cyclic redundancy check. So this is what my CRC is, which I wanted to append to my data. So you very well know what is my data. 1 0 0 1 is what my data bits are, and in addition I will have 3 bits of CRC. Initially I had all zeros in the places of CRC. Now I have calculated the value of CRC as 1 1 and 0. So what I will have to do, I will have to add this 1 1 and 0 over here, and then this entire bit is what I am going to transmit, and this entire bit is what I call it as code word, and this code word is nothing but your data plus your remainder over here. So that is how this particular transmitter algorithm will work. So this is what the CRC that will be performed at the transmitter side. So now we will march forward, and then we will see what happens at the receiver side. So now we will see how CRC is being performed at the receiver side. So here I am taking the case that there is no error that is received at the receiver side. I have not introduced any error over here, and then I am going to perform the CRC for the received bits over here. So now this is what the uncorrupted code word that we have received at the receiver side, and then we will have to perform a long division method for the received bits. And we very well know that the long division method has to be performed for the received bits, and the received bits are 1 0 0 1 and 1 1 0. And then it is very much important to note down that we will have to use the same divisor polynomial what we have used at the transmitter side. So here in our case, the divisor polynomial is 1 0 1 1, and it is important to use the same divisor polynomial because the divisor polynomial is shared between the transmitter and then the receiver as far as CRC is concerned. And now we will have to perform the same long division method as we performed at the transmitter side. So just to keep you reminded, wherever I perform the multiplication operation at the long division method. Here in CRC we will have to perform the logical AND operation, and wherever I perform the subtraction operation in long division method, here in CRC I will have to perform the logical XOR operation over here. So with this note, let us proceed and see whether the code is detecting if there is any error or not. So as usual, it goes for one time. So performing bitwise logical AND operation, I will get 1 0 1 1. So that with this I will be getting 0 0 1 0, and then bringing down this particular one I will get 1. We can neglect this particular bit, the first bit, and then we have experienced that the MSB or the leftmost bit is equals to 0. So whenever we experience the MSB is equals to 0, we will have to add a 0 on the quotient, and then we will have to perform the logical AND over there. If I perform logical AND between 0 and then the divisor, I will get all 0 values over here, and then I am going to neglect this value anyhow, so that I am going to perform the XOR operation for the last 3 bits over here. So I will get 1 0 1, so that I can carefully bring down this particular 1 over here. So I will get 1 0 1 1. So it goes for one time, and then it is 1 0 1 1. So what I am going to get is I am going to perform an XOR operation for this, and then this bit is going to be neglected, and then I will get all zeros over here. And even though if I bring down this particular 0 over here, it is all zeros. So I experienced an MSB is equals to 0. So what I have to do, I have to do a 0 over here, and then perform an logical AND operation between 0 and then the divisor. Again I am going to get all zeros. I am going to neglect this, so I am end up with all zeros. So there is no point of proceeding over here, and we don't have any bits to bring down over here. So now we can clearly observe that the remainder what we have obtained over here is all zeros. So technically we call this as syndrome in CRC is concerned. So if the CRC is all 0, then it represents there is no error in the received data. So that is how the CRC system will identify if there is any error or not. So now what we will do is we will just march forward, and then we will see what happens if an error is introduced and whether CRC can able to detect the error or not. So that is what going to be the next case. Over here in this case we can consider this as case 2, where I have manually introduced an error over here. So as you can see, this is what the received bit is, and this is what actually supposed to be 1, but I have replaced it with 0 over here. So as far as this case is concerned, the data word or the corrupted code word what we have received is 1 0 0 0 and then 1 1 0. So now I am going to use the same divisor polynomial over here, and then it goes for one time. So 1 0 1 1 is what I will get, and then if I perform XOR operation, I will be getting 0 1 1. I can bring down this one over here, so I will get 1. So I have experienced MSB is equals to 0. So I will have to put a 0 over here and perform a logical AND operation between 0 and then the divisor. So I will get 1 1 1 over here, and if I bring down this particular one, I will get all ones, and then it can go for one time. Performing logical AND operation between 1 and the divisor, I will get 1 0 1 1, and by neglecting this particular bit, I will get 1 0 0, and I can bring down this particular 0 over here, and then it again goes for one time. Performing AND operation between 1 and the divisor, I will get 1 0 1 1 over here. Correct. So if I neglect this particular bit, I will get 0 1 1, and this is what we call it as remainder, or in CRC term we call it as syndrome. We call it as syndrome. As you can clearly see that the syndrome is a non-zero value over here now. So which means any non-zero value in syndrome, that represents there is an error in the received data, and then this particular code word will be discarded for being for the process. So that is how the CRC will detect the errors in the received data stream or not. So whereas for the sake of example is concerned, we have taken only the 4-bit data word, and then we just understood how exactly the CRC is being working. But in real-time situations, the CRC is of very standard format, and these are all the standards or before getting into the standards, we will just look out the characteristics of a good divisor polynomial. This is why I earlierly mentioned that we do not have the freedom of choosing our own divisor. So these are all the 4 characteristics which a divisor polynomial should satisfy. So the first criteria is it should at least have 2 terms in it over here. So at least it should have the coefficient of x and then the x to the power of 0. So the coefficient of the term x to the power of 0 should always be 1. It cannot be 0. It cannot be 0. So it should not divide the term that is x to the power of t plus 1, where t is any value between 2 and then the n minus 1, where n is nothing but the total number of bits in the data. And then it should have the factor of x plus 1, which is nothing but it should be divisible by the polynomial x plus 1. So these are all the various characteristics which my divisor polynomial must have, or it must satisfy. So we will actually have different standards of CRC polynomial. So if it is an 8-bit CRC, then this is what will be the standard divisor polynomial that we will be using, and for 10-bit this will be the polynomial, for 16-bit this will be the polynomial, and for 32-bit this is what will be the polynomial over here. And then the last column in this table, which actually represents the various applicational areas for the suitable CRC length. So that is all about the CRC code, or the error detection code or cyclic redundancy check code in this particular video. I hope that now you will be very clear with how CRC transmitter algorithm is working and how CRC receiving algorithm is working, and how CRC can able to detect the errors that is occurring in the transmitted bit stream. So with this, I am going to end up this particular video, and then I am going to see you in the next particular video. So until then, it's a bye from Jai. So happy learning.